We are live. Yes, Professor Bharadwaj, we are live.
Susagatam, Namaskar, Kemcho, Adavarza, good morning, good afternoon, good evening, depending upon which part of the world you are. आप सभी का
Yes, Professor Bharadwaj, we are live.
it has started now or before? I think there's echo coming.
Yes, someone's YouTube is on. Actually. Someone's you
Can you just
please
undo it and do it again? Bushit?
mute.
I think there was some issue somewhere.
No, I think some mute. They were not all were muted. I think now if everything is muted, you can start again.
Shall we start again?
Yes.
Susagatam, Namaskar, Kemcho, Adavarza, good morning, good afternoon, good evening, depending upon which part of the world you are. आप सभी का PRL के अमृत व्याख्यान में स्वागत है, अभिनंदन है. Very warm welcome to you all from me, Anil Bharadwaj, for PRL का अमृत व्याख्यान. This is the 25th episode of series of Vyakhyaan, which is being organized as a part of PRL's 75 years of legacy and history in fundamental physics and space sciences. Established in the year 1947 by father of Indian space program, Dr. Vikram Sarabhai, the PRL's Platinum Jubilee coincides with India's 75 years of independence. So it's a joint celebration of development of science and technology in India by PRL under the banner of PRL Ka Amrit Vyakhyaan. Today we have yet another distinguished speaker, Prof. G.S. Agarwal, who is going to deliver his Vyakhyaan on squeezed light from abstraction to real life applications, sensing and imaging well beyond standard quantum limits. Professor Agarwal needs no introduction to the audience. He has two commonality with me. Firstly, he is alumnus of Banaras Hindu University like me, and he is a former director of PRL during the year 1995 to 2005. With this, I welcome Professor Agarwal, and I request my colleague to introduce formally Professor Agarwal. Over to you. Hello.
Yeah. Professor RP, you are there. Professor RP Singh. Yes.
You can save time by cutting down on the introduction.
RP, you are not audible.
RP, you are not audible, please.
RP, you are muted.
Your Professor RP Singh, we are not able to listen to your voice. You may unmute. I think he's.
RP, there may be a problem in your microphone. Hello?
I think the director has already introduced me. That's good enough. So we can start with the program.
Yeah, just before we start, I think I'll do, I'll just pitch in here. It's indeed a great pleasure and honor for us to introduce our speaker for the day today, Professor Girish Agarwal, who is an FRS and alumnus of Banaras Hindu University. He did his PhD from Rochester University, USA, He then returned to India and worked at TIFR before accepting an invitation to establish a school of physics at the Central University, Hyderabad. He was the director of PRL during 1995 to 2005 and has nurtured an internationally respected school of quantum optics in India. He has been at the Oklahoma State University, USA as a Nobel Foundation Chair and Regents Professor. He is presently a faculty at the Institute of Quantum Science and Engineering, Department of Biological and Agricultural Engineering and Physics and Astronomy, Texas A&M University. Professor Agarwal is an internationally acclaimed for his contributions to quantum optics, laser physics, and statistical mechanics. He is a recipient of the S.S. Bhatnagar Award, the Humboldt Research Award, the G.D. Birla Award, the M.N. Saha Birth Centenary Award, and the Albert Einstein Professorship of the Indian National Science Academy. He is a Fellow of the Royal Society, the American Physical Society, the Optics Society of America, the Indian National Science Academy, the National Academy of Sciences, the Indian Academy of Sciences, and the World Academy of Sciences. He has published more than 700 papers in peer-reviewed international journals, including peer-reviewed articles and research monographs. He has authored a book on quantum optics published by Cambridge University Press. With this brief introduction, I welcome Professor Agarwal to deliver the 25th PRL Amrut Vyakhyaan. Professor Agarwal, please.
Okay, so, so I'm audible, right?
Yes, sir. You're perfectly audible.
Okay. So it's a great pleasure to give a lecture on the occasion of the 75th anniversary of the foundation of PRL. So I'm grateful to the director Anil Bharadwaj and Pallam Raju for the kind invitation and the introduction. For me, it was great honor to have served PRL as director for 2 terms. I have fond memories of my time at PRL, and I must say that every time I visited PRL after my retirement, I have enjoyed the visits thoroughly. The directors have been very good hosts to me. Okay, so let me start by saying that we all know very well that how the discovery and the availability of the lasers changed completely the character of spectroscopy. For example, the Raman spectra could be taken in no time, enabling all-round applications of Raman spectroscopy. The laser fields, as we understand, although the way the laser fields are produced has origin in quantum mechanics, but the characteristic features of the laser fields are almost for all purposes classical in nature. Now, in the last decade or so, people have been thinking how to make use of the quantum character of light, whether there is any advantage that we can gain by using the quantum character of light for spectroscopic and other applications. And in fact, one has found both theoretically and experimentally that there is indeed great advantage if we have quantum sources of light which would give what some people started calling quantum supremacy, but many of us prefer to use the word quantum advantage rather than supremacy. So clearly this implies that there is need to build up sources of quantum light, not just the laser sources. And so in my talk, I like to tell you that what are the newer spectroscopic capabilities if we replace the coherent source, that is the laser, by a source of quantum light. There are many different kinds of quantum light sources. There is the squeeze light source, and I have an experimental program at Texas A&M University, and we have built up the squeeze light source at Texas A&M University, and so much of my talk would be devoted to the demonstration of quantum advantage in absorption spectroscopy, which is a very versatile form of spectroscopy used in almost all the fields. Then the advantage in Billion and Raman spectroscopy, leading to applications in quantum imaging and quantum microscopy. There is another kind of source which is quite a versatile source, and these are the SPD sources, parametric down converter sources. These produce entangled photons. So depending on the application that you have in mind, you can use the squeeze light source, or you can use the source of entangled photons. And again, some of the applications of these sources would be in enhancing the two photon absorption processes and the Raman processes. These kind of sources can also give you enhanced frequency time resolution in nonlinear spectroscopy. Next slide, yeah. So let me just start by telling you how most classical sensors work. So you have some medium here, and you bring in a coherent source of light, and you can look at either the transmission from this medium, or you can look at the scattered photons from the medium. When you look at the transmission, you can look at the transmitted intensity, or you can look at the phase of the transmitted light, and you can scan the transmission as a function of the intensity of the input light, or as a function of the wavelength of the input light. And this would give you information on the absorption characteristics of the medium, which in turn gives you a lot of information about the underlying physical processes going on in this medium. For example, the density of particles, it can tell you the resonant transitions in the medium, can give you information on oscillator strength, relaxation parameters, etc. If there are defects in the medium, this would lead to scattering, and so the scattering amplitude also becomes a sensing capability. Small perturbations of the medium are of special interest, and therefore the question arises that how small values of phi and how small values of alpha can be detected. So this is sort of a generic sensor, and you can build up many different kind of sensors based on this. There are other kind of sensors which are very commonly used. These are called plasmonic sensors, are sensors based on nanoparticles, based on the electromagnetic induced transparency. So there are a whole lot of sensors depend on various processes, but typically you are looking at either at the transmission or at the scattering. Next. Okay, so now let's look at that what's going to be the sensitivity of these measurements. And so the measurements done with photodetectors, that's what we use most of the time. No, go back to the previous one. Yeah. So, and we know that the photodetectors work by ejection of an electron due to each incident photon with some probability. And hence the photodetector measurements are subject to the photon number fluctuations inherent in a laser field. So for classical sensors, we are using laser field, but we are using photodetectors for detection, and these are sensitive to the photon number fluctuations. And the laser field, although it's a coherent field, has photon number fluctuations. So the photon number fluctuations in the laser beam are Poissonian in nature, and therefore all the classical measurements are limited by what's called the short noise limit or the standard quantum noise limit. And this limit is defined by the intrinsic Poissonian fluctuations of the laser beam. So please keep in mind that when you talk of the standard quantum noise limit, it assumes that you have gotten rid of all other technical sources of noise. Once you have gotten rid of all the technical sources of noise, you still have the intrinsic fluctuations which are associated with the laser beam. So the quantum light, so we'll see that how the quantum light can overcome the standard quantum noise limit. Next slide, please. So that was the situation with the measurements of the transmitted amplitude. For the phase measurements, you need to have an interferometric device, and this is the Mach-Zehnder interferometer which you would use for the phase measurement. And you can show that these phase measurements have a sensitivity which is again limited by this limit, which goes as 1 over square root of the number of photons. And this factor comes from the fact that the photon numbers in the laser beam are Poissonian, and for a Poissonian distribution, the variance is equal to the number. And so that's how you get this square root of n. Next slide, please. Okay, so more quantitatively, let's say this is the transmission measurement. You come in with a coherent field, which is the laser. The output is also going to be a coherent field. And so the number fluctuations in the output will be proportional to the number, or the noise would be the variance in the signal, and the variance in the signal would still be proportional to the square root of this. And so signal to the noise ratio is square root of the signal, and that is the short noise limit, and we want to beat this short noise limit by use of quantum light. Next one. Okay, so this has a simple calculation where now the calculation is done by using the quantum source of light. So you have an input quantum source, you have a transmitting medium with some absorption, and we look at the output quantum field. And we want to find out that what is the best sensitivity that we can get for this absorption parameter. And the way we can define the best sensitivity, we can look at the number fluctuations in the output field. Then we can look at the average number of the output photons and the change with respect to this absorption parameter. So this is one of the standard ways to define the sensitivity of measurement. So experimentally you measure this quantity, you measure the signal, take the derivative of the signal, and from that you estimate this parameter delta alpha, which would be the sensitivity parameter. And so you can do a fairly general calculation in terms of the absorption and the fluctuations in the input field. So these are the number fluctuations in the input field. This is the mean number in the input field divided by the input number. And now from this expression, it would be clear to you that delta alpha would be smallest, or the best possible measurement that you can make would correspond to this quantity becoming 0. So if there are no number fluctuations in the input field, then you have the best measurement of the absorption parameter. And so you need to have an input field with no number fluctuations. Now such input fields are the fields which have precisely a given number of photons. And such fields are extremely hard to produce. You can think of a field which consists of streams of single photons. For that case, this would be 0. That can give you the best measurement. But such a field is extremely hard to produce, and the experimental groups are working on how to produce single photon sources. Next slide. So now I like to introduce the idea of a squeezed light, and theoretically this was studied in around mid-80s, extensive work on this subject, theoretical work in those days. Sorry, previous one. Yeah. So if we think of a coherent state of light or the laser fields, we look at the fluctuations in the laser field in terms of the two quadratures. So this is kind of electrical engineer's language which is used here. One defines the quadrature of the light field X and the quadrature of the light field as Why? Now, in simple language and at the classical level, the electromagnetic field is complex, and you can look at the real and imaginary parts of the complex field. So these quadratures, in a sense, correspond to the real and imaginary parts of the quantum field. And so these are fluctuations, these are the quantum fluctuations. And for the laser beams, so we talk of the laser beams and everybody thinks that these are highly coherent fields and nothing fluctuates there, but there are intrinsic fluctuations which are of quantum origin. So you have these fluctuations, and so around the mean value you have little blob there, this circular blob which corresponds to these fluctuations. And so the idea of squeeze light is to change this blob to this or to this. And so one will say in this picture that in this direction or this quadrature you have squeezed the fluctuations. And in this case you will say that this is the quadrature that you have squeezed the fluctuations. Okay, now we know how to produce such a source of light. Next one. Okay, so this indicates that what is the advantage of this kind of light in interferometry. So this is the Mach-Zehnder interferometer which we use to measure the phase phi. So what we do now, the proposal was to put a squeeze light on this port of the Mach-Zehnder interferometer. And then it turns out that we have a phase sensitivity which is improved by the squeezing property of this quantum light. And this is the improvement factor. So depending on this R parameter, which is called the squeezing parameter, and more engineering language, it is expressed in terms of dB. And so the dB scale is defined by like this, 10 log 10 e to the power 2r. So if you have a very moderate amount of squeezing, this is very easy to produce 3 dB squeezing. You already get an improvement by a factor of square root of 2. So that itself is quite significant. And if you can produce larger squeezing, then you can improve the phase sensitivity measurement. And the current record, which is held by the gravitational people in Hanover for squeeze light, is 15 dB. That is the world record. Next slide, please. Okay, so that was the single mode squeeze light. The more common one is what's called two mode squeeze light, and this is produced by the process of four-way mixing, which I will describe in a minute, or also by the down converters, if the down converters are operated in high gain mode. So these would produce squeeze state only in the high gain mode. So what is this two mode squeeze state? What we say that you have pairwise quantum entangled state. So if you think of two modes, so if a photon is there in this mode, then a photon is also there in this mode. So these two photons occur together. If this mode has two photons, then this mode also has two photons. So there are very strong quantum correlations because of this character. And please note that this is the wave function of the radiation field. So at the wave function level, we have this character for the state, and this is called quantum entanglement. In case of quantum entanglement, we cannot factorize this state in terms of the state of mode A and the mode B, as would be quite clear from these pictures. So because of this character, there are strong correlations. Next slide. Okay, so now I like to tell you how we produce squeezed light. And one way to produce squeezed light is to use atomic sources, atomic vapors, and we use the rubidium-85. So the process which is illustrated here is called the four-wave mixing. So see, there are four electromagnetic fields here, and these are the two hyperfine ground states of the rubidium-85. So you come with a strong pump, So this pump can produce a photon here. Once you produce a photon here, then you take another photon from the pump and produce this new photon. So see, these two blue photons, these are coming from the strong pump beam. The two blue photons are converted into one red photon and one green photon. So this is called four-wave mixing because you have four photons which are involved. And the probe, and this one is called conjugate, which is in the vacuum state. They come at a small angle to this, to the pump field. For illustration purpose, I have shown a large angle, but actually typically it would be like few degrees to the pump because there are certain conditions which are to be satisfied. Another thing which one has to keep in mind, that one has to use the proper frequencies of these fields so that you do not hit any of the resonances in the atomic medium. Because if you hit any of the resonances, then the fields are going to be absorbed. And the quantum light is extremely sensitive to absorption, and therefore we have to make all possible effort to avoid absorption as much as possible. Now, you can do a theoretical calculation and then you can show that under the experimental conditions, this whole thing can be described in terms of an effective Hamiltonian. So A and B, these are the quantum fields. This one is a quantum field. You are not applying this field. The red one is generated from vacuum. So anytime you generate something from vacuum, it has to be a quantum field. Probe is also a quantum field. So green and red are quantum fields. And so this whole process can be described by an effective Hamiltonian. And this effective Hamiltonian leads to two-mode squeezing. Next slide. Can you click again on the same slide? Go on clicking till it says the full slide. No, previous one. Okay. So this effective Hamiltonian, it it gives you solutions of this kind, and this parameter R would now be the squeezing parameter, which would be related to this coupling constant in the Hamiltonian and the interaction time with the medium. So let me now show to you that what are some of the important characteristics of the generated fields. Next one. Yeah, click, go on clicking till you see the full slide. Okay. So, so we can look at the Prof field, and we can look at this conjugate field, and we can look at the fluctuations in each of these fields. So fluctuation in this, fluctuation in this, and what you discover that the fluctuations in each of those fields, these are amplified because of the four-way mixing process. There is a gain which is due to the four-way mixing process, and these fluctuations are amplified. That gain part is also apparent if you look at the solution. Anytime you have cosine hyperbolic and sine hyperbolics, you have gain. Next one. Yeah, go on clicking. Okay, so no, previous one. Yeah. So each one of these have enhanced fluctuations, but now we look at the difference. So we look at these photon numbers here and photon numbers here, and look at the fluctuations in the difference between these two fields. So photon number fluctuations in the difference, these turn out to be less than the photon number fluctuations if you had coherent fields here. If this was a coherent field of this with the same photon number, this was a coherent field with the same photon number, and you look at these difference fluctuations, then those difference fluctuations are higher than what's produced by the four-way mixing process. So this is the most important thing to note, that while each of these are more noisy, the difference is much less noisy. And that is the property we are going to use in all the applications. Next slide. Yeah, so this is what is a theoretical graph, that the ratio. So we look at the fluctuations in the difference for the squeezed light, fluctuations in the difference for coherent light, and the ratio. And you can see that these go down with increase in the four-way mixing gain. Next one. Okay, so this is the experimental result, that this is the short noise limit, or the standard quantum noise limit, and the squeeze light, the two-mode squeeze light that we produce, has this characteristic, the blue curve, and this is the noise power in the difference of the photon numbers in the two beams, and that is what is much lower, and we get a squeezing about 6.5 dB. So this is the intensity difference squeezing. Next one, please. Okay, so some of these characteristics of the light that we produce, I'll then describe quickly. Next one. So how to characterize all this quantitatively? So we introduce this parameter sigma, which is the fluctuation in the difference divided by the corresponding fluctuation for a coherent light, which would be just the sum of these two photon numbers. So for the coherent light, the sigma parameter would be 1, and for the quantum light, the sigma parameter would be less than 1. Next slide. Okay, I leave this out. Next one. That was just a mathematical proof that that sigma less than 1 characterizes the quantum nature of light. Okay, so now some measurements which are done with the EMCCD, and so these are the temporal patterns, conjugate light, the probe light. The probe light is stronger than the conjugate light because we are putting an input seed there. Okay. So now we can use these EMCCD recordings, and the durations are indicated here, and this is the separation between these two intervals. Next one. Yeah. So the top one, we have two independent coherent states. The fluctuations of these two independent coherent states. This one, we take the sum of the photon numbers in the two coherent states and the differences. And you see the fluctuations are same. So the left panel is for coherent states. The right panel, this would be for the two mode squeezed state. So one of these, the green one is the conjugate and the blue one is the probe. So these are the fluctuations in each beam. As I indicated earlier, that the fluctuations in each of the beams are large because of the amplification. Whereas if you look at this one, where we have subtracted and added the conjugate and probe, and now you can see that if you look at the difference of these two, which is the red curve, so the fluctuations in the difference are squeezed. So that is the signature of the intensity squeezing, whereas the fluctuations in the sum are higher. So this is the scale of the fluctuations in the difference, which is characteristic of the squeezing. So we can characterize it quantitatively from this data. Next slide. Yeah. So this is the sigma parameter, which I mentioned to you earlier. And in the data is defined for two consecutive intervals. You take one interval for this difference, subtract from the next interval, and that's to get rid of some of the technical noise. So this sort of ensures that the technical noise does not contribute to this sigma parameter. So the origin of sigma in that case would be of quantum nature. If you look at this green curve, so that's for the intensity difference, and this is the coherent case. Okay, next one. Yeah, so now we can apply and demonstrate quantum advantage in absorption studies. So what we will do, suppose we remove this sample from here, and this is our just production of the two-mode squeeze light. So what we would study that how the intensity difference squeezing changes by the introduction of this sample which has a small absorption. Of interest is to measure the small absorption. If absorption is large, then it's of no interest because you can use any of the standard methods. Okay, next one. So first we theoretically computed and looked at this quantum advantage factor as a function of the absorption, because you have optical losses in each of the beams, and so you have to calculate the quantum advantage factor taking into account the optical losses in each of the beam paths. And if you see here this region, so you can get something like a 3 dB quantum advantage if the optical losses are negligible. If the optical losses start becoming more and more important, the quantum advantage goes down. Next one. Well, we can go to the next one. Yeah. So by looking at the changes in the fluctuations in the intensity difference, we calculate the quantum advantage, and the dots here are the experimental data, and the solid curve is the theoretical prediction, and this would be for the coherent light. There is no quantum advantage, so that's why for coherent light you get 0 value here. And so one finds about 1 dB in this range quantum advantage. And if you make correction for the unavoidable losses, then this 1 dB would translate into 3 dB of quantum advantage. So we demonstrated in this experiment a very clear quantum advantage in absorption measurement. Look at this range. This is less than 10% absorption. And that's what we are interested. We are not interested in that larger values of absorption. Next slide. Okay, so these are the results from other groups who reported quantum advantage using different types of quantum light. So this first one is the result from Bristol group. They got a quantum advantage about 0.9 dB. And this is from Oxford group. They have a smaller quantum advantage, about 0.25, 0.3 dB. The difference is that this quantum advantage that the Oxford group is reporting is in the gain measurement, whereas what Bristol is reporting is in the absorption, and our measurement is also for absorption. Okay, so let me now turn over to a different class of problems and demonstrate quantum advantage in nonlinear spectroscopy. Next slide. So we actually, since I was hired by Texas A&M University to develop a program in bio applications of quantum light and biophotonics. So we are collaborating with the biomedical engineering department, and our colleagues there, they have done a lot of work on billion spectroscopy, applications of billion spectroscopy in biomedical imaging. And so like it says, while many properties of the muscle and the loss of it have been studied, the viscoelastic properties before and after MD have received little attention. Billion spectroscopy can be used as an alternative, non-destructive, non-invasive method to distinguish between tumor and the healthy tissue. The mechanical properties of malignant tumors differ from those of surrounding healthy tissue. So our biomedical engineering program has a large program on the applications of classical billion scattering, and we are trying to understand that if we use quantum light, then what kind of quantum advantage we would have. Next slide. Yeah, so this one just this tells you the basic mechanism of billion scattering. So in a medium, you have these acoustic phonons. You come in with a pump field. So this is a strong pump, direction K, frequency omega. Acoustic phonons have a wave vector Q and frequency omega. And you can look at the scattering at an angle theta. So this is the billion scattering, which occurs in this direction, K minus Q omega minus omega. The scattering angle gives you a relation between the billion frequency modes or the frequency of these acoustic phonons, the velocity of sound, this is the velocity of sound, and is the refractive index of the medium. So this is a well-known relation in billion scattering. And for billion scattering, the back scatter direction is the most preferred one. So if this is the pump, you look at in this direction. Okay, we are interested in what's called the stimulated billion scattering. So in stimulated billion scattering, you bring another field in this direction. So you apply a probe, we will call it a probe, or the stimulating field, and we would look at addition of a photon in this field. So pump photon will scatter from these phonons a photon into this field, and therefore this field will grow in time. So that is called the stimulated billion scattering. And what we would study, we like to understand that if we replace this stimulating field by a quantum source of light, then what is the advantage? Next slide. Okay, so we studied this is the standard billion spectrum of water, and water is the most important for biomedical applications. So this is the billion spectrum of water, and this is the well-known billion gain peak at 5 gigahertz. Please note that these peaks are narrow, like 20-30 megahertz. So you have to do a lot of high resolution work to see these narrow peaks. And the intensity of the billion signal is proportional to the power of the pump as illustrated here. So this is the classical billion scattering spectrum. Next. Okay, so here is the schematics of what we want to do with the squeeze light source. So this part, that was our generation of the squeeze light, quantum light. And now we put our water sample here. This one of these two beams we will use as a probe. And in order to see the billion scattering, we need a pump. So we need to bring another pump from this side. And these two have to be almost 180 degrees of each other. And what we would look at, changes in the fluctuations in the intensity difference to gain quantum advantage in billion scattering. Next one. Next. Well, this is a complicated experimental setup and it will take some time to describe the whole thing. So let me just move on to the next one with the results. Next, yeah. So there are two sets of plots here. So one data, this is the pump power, pumping the water sample. This one is at 36 milliwatt, this is at 7.5 milliwatt. And now we take the billion signal which is obtained by a spectrum analyzer. So what it means that you sit on the billion peak, look at the spectrum of fluctuations of the billion gain peak. And so the fluctuation spectrum is shown here. The big one, no, this big one is for squeeze light when you are sitting on the gain peak. And this green one is for the case when you move away from the gain peak, but you are still using the squeeze light. The red one is for you replace the probe by a coherent source sitting on resonance, and this one you are off resonance. Okay. So the most important thing to note here is this noise floor level. So with coherent light, this is the noise floor level. With the squeeze light, this is the noise floor level. And therefore what it implies that if you have a signal which is buried in noise, then you can use the squeeze light to see the signal. And that is what we illustrate here in this data. So this is the noise floor with coherent light. And at this level of pump power, remember that the billion signal is proportional to the pump power. So at this level of the pump power, the signal is below the noise floor. And therefore, with coherent beams, you would not see such a signal. Whereas with the quantum light, you can clearly see the signal because you have pushed down the noise floor. And this amount of pushing down the noise floor is about 3.5 dB. So that is the quantum advantage that one gets in billion spectroscopy if you use intensity difference squeezed light. So this 3.5 dB is quite a significant quantum advantage. Okay, so the question arises that why you want to use the lower pump powers. The lower pump powers are desirable because if you are working with the biosamples, you don't want to apply too much power. If you apply too much power, the biosample would be killed. And currently, like Department of Energy has floated several programs, application of quantum light to biosamples, and they are all interested because they are trying to push down work at much lower powers so that you don't make appreciable changes in the biosample due to the applied power. So how much time I have, because I'm going slow because of also partly because I'm not in control of the slides.
No problem, sir. We can go ahead. You can 10-15 minutes more you have.
Okay.
Yeah.
Okay, so next slide, please. Okay, next one, I'll just skip some of this slide, the key point I have indicated. Next one. Okay, next one. Okay, so we have demonstrated the advantage, the application of this quantum advantage in imaging, and just as a proof of principle, we used a glass piece of this shape and looked at the results with coherent light and with quantum light. And with quantum light, we can clearly see this object. So we can see clearly the object, whereas with coherent light, at the level at which we are working, we cannot image this. So we have demonstrated in the same paper which is on archive, submitted about a month ago, the distinct quantum advantage in imaging. Next slide. So since we are collaborating with our biomedical colleagues, they are making some samples for us, and they wanted us to study using our quantum source of light some cancer cells. So they produce a sample, and we like to study their sample using quantum light. So for example, for the sample that they have given, the colony, the cell colony has a lot of water content, and the hydrogel has no water. And since we are using the billion scattering of water as our signaling agent, so that's why they have put the cell colony in hydrogel. And if you look at the billion spectra, the traditional billion spectra, so this is for the hydrogel, the green one. The blue one is the water, and the red one is the cell colony. Next one. So this is just a very preliminary data on these samples. So this one is using the coherent light, and this one is using the quantum light, and you can see if you compare these two, you can see much higher contrast here. So a part of the cell colony is being analyzed here with coherent light and with the squeezed light. Okay, next slide. Okay, before I conclude, I also like to say something about other types of quantum light. And we had actually discovered many years ago, as you can see, this was a paper in 2004 when I was still at PRL. And we discovered quite an unusual feature at that time, that if you look at two photon transitions, it's a two photon transition, one photon, and you have two atoms, you are going from this ground state to the excited state. So it was known that if you do this kind of two photon transitions with the coherent fields, then under certain conditions, nothing goes to this doubly excited state. In other words, the two photon transition was disallowed. And one could explain this very nicely in terms of the various quantum mechanical paths which are allowed according to the second order perturbation theory. And one discovered that there was a nice interference between all these paths. There were 4 different paths for two photon absorption, and they interfered with each other, giving rise to 0 doubly excited double excitation. So at that time we had discovered that instead of using the coherent light sources, if we use entangled photons, then we discovered that this double excitation is possible. And it turned out that out of these 4 paths, 2 paths can be killed. And since the 2 paths got killed, there was a double excitation. So this became actually quite a tool for people working with the quantum light in a spectroscopic context, that higher order processes have lots of quantum paths which determine the efficiency of higher order processes, and therefore you can use quantum light, and the quantum light can control the efficiency of the higher order processes. And so we were collaborating recently with a team of experimentalists in Zhejiang University, and this team works with the superconducting qubits. So this theoretical prediction was verified using the superconducting qubits in this paper, which was published year before last now, in 2020. So exactly this prediction that the entangled light could allow a transition which otherwise is not allowed. Next slide. Yeah. So before closing, I'll mention quickly the down converter sources of entangled photons, and these sources people have used quite a bit, again in two photon absorption spectroscopy. And what particularly the Goodson group from Michigan, he has pioneered this, and in a whole series of experiments, he has demonstrated the great advantage of doing two photon absorption in spectroscopy at very low light levels produced by the SPDC sources. So SPD sources produce an entangled photons. You have photon in one mode, photon in another mode, and there is a spectral function, and this spectral function does not factorize. And you can calculate what this function is according to the characteristics of your down converted source, and also depending on whether the down converted source is pumped by a pulse laser or is pumped by a CW laser. Next slide. Okay, so the down converted source, you can operate in different regimes, and the most conventional regime is this one. So the two photons two entangled photons which you produce, they are called anti-correlation. One says that there is an anti-correlation between the two down converted photons. Whereas this one shows a correlation between the two down converted photons. You can operate the down converter. It's more difficult to do so, but you can produce a correlation also between the two down converted photons. And we can use, it turns out we can use this for doing two photon absorption, and we can use this for doing Raman scattering. Next slide. So now this is a single atom problem. You are doing two photon absorption in single atom, and what turns out that there is an enhancement by using these entangled photons. So the excitation amplitude is enhanced by this ratio. So this is a ratio of the two line bits. And can we go back to the previous slide again? So that ratio is just the ratio of this bit to this bit. And so this bit divided by this, that's what enters in the two photon absorption. Next one. So the photon anti-correlation is useful for the two photon absorption enhancement, and that is what Goodson has been using for last 10 years. Next one. And in the Raman scattering, so this is our new, very new prediction in Raman scattering. And again, we have shown that there is an advantage of using the entangled photons. And again, you get this kind of a line bit factor. And please go back to the previous and the previous one, previous. So for Raman scattering, again, this ratio is important. The ratio of this bit to this bit. And that's what determines the enhancement in the Raman scattering. Next one. Next one. Okay, so we can produce enhancement, and these results are very, very new. And we have another effort going on where in future we would like to verify some of these predictions of the enhancement of the Raman scattering cross sections using quantum light. So this would be a big thing once it is demonstrated, because as you all know, the great utility of Raman scattering in all kind of applications. So I think this is probably my last one. Next one must be the conclusions. Yeah. So what I've shown newer spectroscopic capabilities. If you replace the coherent laser source by a quantum light source, which could be squeezed light source or the source of SPDC photons. Specifically, I demonstrated quantum advantage for absorption spectroscopy, and there are various versions of the absorption spectroscopy. We have two graduate students working right now to demonstrate quantum advantage in plasmonics, Billion scattering, we demonstrated quantum advantage. We are moving to imaging of biosamples. So that's going to be major effort in future. And quantum pathways can be manipulated. Two photon absorption enhancement that has been experimentally studied extensively. Raman process enhancement, that's something very new. Hopefully in future, we would demonstrate experimentally. We have another new theoretical work posted in this paper where we have shown, this is another kind of spectroscopy called CARS, again extensively used in applications. It's called Coherent Anti-Stokes Raman Spectroscopy, and we have demonstrated the utility of the SPDC sources in cars in getting much higher frequency time resolution. Finally, going beyond quantum light or beyond light, there also has been a lot of activity on mechanical oscillators. So I, in the past, have worked on squeezing properties, producing squeezing of the nanomembranes. Recent applications, particularly from the group of Vineland, who got Nobel Prize some years ago, they are looking at the squeezing the motion of the ions. So this is the center of mass motion of the ions, and they are looking at the capabilities, enhanced capabilities for displacement measurements. In other words, very, very small motion of the ion you can measure. And in one of the recent papers which just appeared in Science, they have demonstrated a 9 dB advantage by using the squeezing of the ionic motion. So instead of using squeeze light, demonstrating quantum advantage with squeeze light, this is an experiment using the demonstrating quantum advantage using squeezing of the ionic motion. Okay, so thanks very much. It has been pleasure to give this talk, and if you have any questions, I will be happy to answer.
Thank you, sir. That's a very interesting talk, explaining the perspective about the field and giving the current applications. And this is basically the field. Perhaps whole world is looking forward to go for quantum advantage. Now we have a couple of questions in the YouTube chat box and also in the WebEx meeting. But before going reading out those questions, I'll ask if there is any question from the panelists in this WebEx meeting. We'll take those questions, then I'll read the other questions from the other portals to you.
Hello,
I think Ashok has some questions.
Yeah, can I ask one question?
Yeah, please go ahead.
Yeah. Hello, sir. It was a very, very enlightening talk. So this is Ashok from IST Trivandrum, actually. So I have one question. First question is regarding this absorption measurement, actually. So you were using 2-mode squeeze light, and then of course one mode you are just using to probe your sample, and other mode you are directly sending to the detector. So I'm wondering, did you use any loss in the other mode? Because what we have done similar experiments, and then what we found that if you introduce loss in the other mode, we get better advantage.
No, we have like we have not purposely introduced loss in the other mode. We have only the optical losses in the optical path,
Yeah.
So those have been taken into account, but otherwise, as far as the sample is concerned, sample is only in the probe beam, let's say.
Yes, yes. That was our experience actually. We were using electronic noise or electronic noise losses in other beam, and then we were doing like a balanced loss system, and that was anyway that was giving a better advantage. And other point regarding the same thing is, are you planning to look at like the single mode advantage? Because always one like a common question arises that you are comparing two mode squeeze state with the two mode coherent state, and that means like you are into adding like a 3 dB of the noise there. So if you are showing the 3 dB of the advantage, then what will happen to the extra noise that you have already introduced? So are you looking along those lines also?
No, I don't understand what you mean. We have not introduced.
So what I am saying actually, when you characterize standard quantum limit in those kind of system, the standard to characterize standard quantum limit, you replace your probe and conjugate by two coherent states actually.
Of the same intensity,
Same intensity, yes.
Yeah, because that is the comparison.
Yeah.
The classical beams will, I mean, coherent beams, whether you subtract or add, they would always have the same noise.
Exactly.
Right. So that is the benchmark comparison.
Yes, but that noise will be larger than the single state coherent state, right? So that is the question. So if
no, you see, single mode coherent, I mean, single mode we are not using.
yes,
Because that's more difficult to produce.
yes,
Single mode squeezing than the two mode squeezing.
right, sir.
And so that's why we are, as you figured it out, that we are looking at the intensity difference squeezing.
Sure, sir.
Whereas single mode squeezing, people look at the quadrature parts.
Yes, sir. Yes.
And, quadratures are much more difficult to study.
Yeah.
Because you have to do homodyne measurements.
Yeah.
And homodyne measurements are extremely complex.
Yes.
Whereas, measurements with a spectrum analyzer or EMCCD or photodiode are much easier.
Sure, sir. Sure.
So that's why we, first of all, we don't have capabilities with single mode. We have not set up those kind of experiments. But
Great.
usually, most people don't do it because two mode is much simpler.
Yeah, that's correct. Just last point. So sir, I would like to know your remark on use of this squeeze light for quantum communication. What is your point on, or what would you suggest along those lines, sir?
Well, the point is that single photons are the best. And if you can have a single photon source, then you are in good shape. But the point is that we don't have single photon sources available.
Yes.
So that's why you look at the other possibilities. And, the other possibility would be these SPD sources or the two mode squeeze light. And so that's why we are working with those sources. But
Sure.
ideal, of course, is the single photon source.
Yeah.
So like recent experiments from Penn's group. Penn is such a big leader in the world.
Sure.
And he had like 70 sources of the two mode squeeze light.
Yeah.
In demonstrating the quantum supremacy. I mean, you can't
quantum
imagine
computing,
this.
yes.
And these are the cavity sources.
Yeah.
So he had 70 cavity sources. I mean, just imagine the amount of work and how many students and postdocs must have worked on that system.
Yeah, sir. I
Just
noticed that one.
unthinkable.
Yes.
I mean, we can think of one or two cavities, but he has 70 cavities lined up with the, producing two modes. Each cavity producing two modes squeeze light.
Yes, sir. Yes.
So I mean, everybody is trying to do things with two mode squeeze light because it's much easier.
Yeah, sure, sure. Thank you, sir. Thank you very much.
Okay. Somebody else has a question, I see.
Yes. Yes, sir. Please.
If I can ask a question, or somebody
No.
else is asking.
Yeah,
Somebody
Professor
had a question. I
Bharadwaj
saw
has
something
raised
in
hand.
the
Yeah.
chat box or something.
So a chat box, Gautam will handle later.
I'll-
I think
yeah.
we can ask.
Acha, okay.
So just one question, this Raman spectroscopy you were showing advantage with entangled photons. So it is dependent, it will depend on number of entangled photons, or just like 2 photons will show the same advantage as 4 entangled photons.
No, two photons shows the advantage, but you have to operate the down converter in a different mode so that the two photons are correlated, not anti-correlated. And some of the experiments on the correlation case, just demonstrating correlation, not an application, but done by what's his name, Torres from IFCO. Torres from IFCO had demonstrated that you can operate SPDC in the correlation mode. And actually I was in touch and trying to see if we can do some collaboration, with this group. So still you have just 2 photons.
2 photons only. Okay, thank you.
And we are talking of stimulated Raman scattering. Keep that in mind.
Okay. Thank you.
Okay. So, is there any more question, Professor Palam Raju? I see your hand, raised hand.
Yes, yes, sir. I was, curious to know about the ionic motion. You said that produces 9 dB advantage. So, what is the reason for that? Well, compared with the optical, quantum, which you have 3.5 dB is what you said, the quantum gain.
Well, they could produce higher squeezing than what we have been able to do. So, if you can produce higher squeezing, then you get better quantum advantage.
So,
And of course, Vineland and all his team, I mean, they are super experimentalists. So,
okay. So it is okay. Thank you.
I see Professor Bharadwaj raised his hand. So please ask the question and then anything if you have.
Thank you, Professor Agarwal, for a very exciting talk and enlightening us on this 20 years of science, particularly in the area of quantum science. My question to you was, can these squeeze lights be used for quantum tweezers?
for quantum
Tweezers,
tweezers,
yes.
well, we have not thought in that direction. So, but presumably for the case of tweezers, the higher the intensity, better it is for tweezer action. And whereas here we are talking of low intensity beams. So, but still there is no harm in thinking aloud and looking at other applications.
Okay, thank you.
I mean, there are people actually, I missed a talk recently. There was a talk. I mean, they are talking of applications in the geosciences area. So I very much wanted to go and attend, but I could not go and attend. But there's a group in Harvard. They are talking of using NB centers in diamond for geosciences applications. And the name of the person is Roger Fu from Harvard. So maybe somebody in your group may want to look at it.
Okay, thank you.
I see one more hand. Yeah, Namit. Please.
Thanks, Professor Agarwal, for an interesting talk. I have probably a naive question, which is more theoretical. in your slide number 15, I think, when you are comparing short noise with the squeezed limit in the experimental thing, as the analyzing frequency increases, the two curves tend to go towards each other. It stops at 4. I was just wondering whether if at least hypothetically we had increased it to 10 or 15, would they merge?
So which case you are talking?
This was there was a slide on which the short noise or the standard noise versus the squeeze limit was compared.
There was a slide where I showed the quantum advantage as a function of the gain of the amplifier.
No, there was another thing which was plotted against the analyzing frequency.
No, analyzing frequency, what happened that this two-mode squeeze light has a spectral characteristic, and at something like in the current experiment 700 kilohertz or something, in that range the squeezing was maximum. As you go away from that frequency, the squeezing comes down, and that is the frequency of the spectrum analyzer, because intensity is nearly constant, and that's why the spectrum has only the low frequency fluctuations.
Okay. Thanks. That's what I was wondering, that it was going away. So probably the squeezing parameter is decreasing and reaching the usual limit then.
Yeah.
Okay, I saw Dr. Prashant having raised his hand. Can you ask your question, please?
Yeah, Professor Agarwal, it's a wonderful talk. Have you looked at the decoherence, the problem of decoherence?
Partly it is implicit there, because all the optical losses in the beam path, they are sources of decoherence.
Okay.
Because there are losses in all the they are very, very tiny losses, but they all add up. So all the optical losses are sources of decoherence, and you would like to minimize those for better results. So I mean, as far as the experiment is concerned, one is not interested in studying the decoherence properties. One is trying to study the quantum advantage.
Yeah.
Quantum advantage would be best if there is no decoherence.
Sure.
But it is implicit. It is implicit in the experiments.
Thank you.
I have one question. Basically, just a quantum radar is something people are just trying. So how do you see this squeeze light being used in quantum radars?
Well, depends on how they set it up, because they can again use one beam, just like you use in the classical radar experiment, and then whatever backscattered data you are looking at, so then you look at that backscattered beam along with the twin of the beam that you send through, to get the scattered data.
Yeah.
So it would be the same principle, except that you are looking at backscattering.
Yes. So now I'll read out all the questions that we have received in YouTube channel. So Bardhan Mungia has asked what discerning mechanical properties we are talking about in malignant and healthy tissues.
Well, we are just looking at this. I mean, I'm not an expert in that area, but what I was told by my colleagues is that the elastic properties of tissue change. And when there is change in the elastic property, then Billion scattering is a good tool to look at those changes.
Yes. So the next question is from Chirag Patel. The main difference between squeezed light and coherent light is squeezed light has coherence property. Means what is the, I think the question is, what is the difference between these two lights?
Read the question again.
So he has written like main difference between squeezed light and coherent light. Main difference
Yeah.
is squeezed light has coherence property. That is the question. So I think he is trying to understand what is the difference between these two
I'm
kinds
sorry,
of.
he didn't understand. So the squeeze light, we are talking of the quantum correlations. Quantum correlations or quantum entanglement. Coherence is sort of a classical property which the laser field has. So the squeeze light has no coherence properties as such. It has quantum correlations.
So next question is from Anju, is our PhD student. So in four-wave mixing, do you need to tune the wavelength of the incident light for rubidium-85 atom, or it could work for any wavelength?
Do you need to
tune the wavelength of the incident light for rubidium-85 atoms, or it could work for any wavelength? So
no? See, we are using the atomic structure of rubidium, and therefore we need to tune close to the P levels, but not exactly to the P level, because we want to avoid the absorption.
yes.
So this condition requires that the detuning from that level would be like hundreds of line bits away. So that is sort of the ballpark how you choose the tuning.
Okay, next question is by Satyajit Patel. He is also our PhD student. Are the output probe and conjugate fields correlated with each other like SPDC photons?
No, that's what we are measuring. You see, I mean, we are looking at the changes in the quantum correlations due to the sample.
Mm-hmm.
So they are still quantum correlated.
Yes. So here is a series of questions, like in slide number 23, why the blue line increasing with the frequency? I don't know that you don't have access to that slide number 23.
No, I can explain. What is that question? Blue line is?
Is a blue line increasing with the frequency? On and slide number 23. So
Yeah, blue line. So when you come to the to the center of the line, gain line, so that's where you have that peak.
So you say that anti-correlated, but his question is in which degree of freedom you are considering for the anti-correlation? Is it transverse or longitudinal momentum?
Well, you see, I mean, in a simple model, you can consider one-dimensional model. And, for most works on the SPDC, we don't worry about the transverse modes. We only look at the longitudinal modes. And therefore, the frequency and momentum are simply related. So when you say anti-correlation, it means that the sum of the two frequencies is very, very close to zero. So omega 1 plus omega 2 is very close to zero. That's anti-correlation.
Yes, yes. So next question is, what is the difference between a probe and a coherent pump?
Probe is also coherent. The pump is a strong pump. We all need to have a strong pump to do the four-way mixing. Probe is a weak probe, but that is also a coherent beam. So pump is a laser, probe is a weak laser.
Okay. So Satyajit, as you love answering the PhD students, so I'll read out his last question. he has stopped his questioning with this last question. Please bear with us. So how the squeezing will change with the degree of coherence? That is the last question he has stopped with this.
As I said earlier, that we are not talking of coherence here. There are different concepts. Coherence is one concept which we use for laser beams. For squeezed light, we don't use the concept of coherence at all because it's not relevant. For squeezed light, what's relevant, either you say quantum entanglement or you say quantum correlations. The two beams are completely incoherent, just like in the SPDC. I mean, you have a full SPDC lab, and so your SPDC photons have no coherence, zero coherence.
Mm-hmm.
Whereas they have a strong quantum entanglement.
Yes. Sir, I will ask a last question from my side. Okay. So, what will be your message to the community in India, those who are working in the field of quantum optics or in this field particularly? And given this, Indians' investment on this field particularly, what are the topics or fields basically scientists should look and which has really means life-changing applications or so in this particular field? So your guidance will really be helpful. It will be helpful for many of us.
Well, I would say that look for an application which is in a totally different direction, so that you make a big mark there. Just like the director was saying that how about the tweezers? Could there be a possibility there? So why not? So if you do an application in a direction in which others have not, done anything, you make a big impact. So that's what you have to see. Yeah.
Thank you very much for your answer, patiently answering all the questions from the students. Sometimes it's a very naive, sometimes it's a very tough kind of thing. It's not tough for you, but for me, I was just thinking from my perspective. So thank you very much for your time. Now I'll just hand over to Lokesh for the next proceeding. Thank you very much.
Yeah. Thank you, Gautam, for very nicely handling the question answer session. And first of all, we are very thankful to the speaker, Professor Agarwal, for excellent talk in the field of quantum optics, recent progress, and applications, particularly in biomedical sciences. Now, I take this opportunity to also thank our viewers who have joined through WebEx and YouTube channels, and also interacting with the today's speaker. And I also thank the colleagues who very nicely, handle everything, question, answer, and interaction sessions. And also, I am thankful to our director, Professor Anil Bhardwaj, Dean, Professor D. Pallam Raju, and our committee, Vyakhyaan committee, Professor Nindita, for all their support to host this excellent Vyakhyaan. And once again, I thank you all for being the part of Azadi Ka Amrit Mahotsav, which is the celebration of India's 75th years. And also a kind of a small announcement that please note that change in timing for the next Amrit Vyakhyaan, which will be on 26th January. So that Vyakhyaan will be also the part of our celebration to the Republic Day. So we'll get back to our original timing, like 4 p.m. IST. So please take note of this. And with this, I propose to close today's PRL Amrit Vyakhyaan session. Thank you all.